Okay, this is number 52 on page 262, and you got to know how to do one like this for the test, just like the bear one. But this is a different kind in that there's motion going on here instead of a static problem. Now, on number 52 says use conservation energy to find what? Determine the angular speed of the spool after the 3 kilogram bucket has fallen 4 meters. Okay, we can do that, but I want to show you an alternate version that I want you to know how to do for the test. There's some more in here like that, like number 70 on page 265. This can be done like this. Number 40 on page 261 will be similar. And so I'm going to show you how to find, first of all, the acceleration of this bucket and the angular acceleration of the spool. And to do that, we have to make a free body diagram, and we have two objects here. We have the bucket, which I'll just make a square. So the bucket, I'm going to make a square. And then we have this pulley. So we'll do that. Right here, and it's got a problem here. All right, to do a problem like this, and this is 3 kilograms, we have to do a free body diagram, just like we did in chapter 4 when we did forces. And we know there's 2 forces on the bucket, a 30 Newton force going downward, and a tensional force going upward. And we know when we let go, this is going to accelerate in the downward direction. Okay, well, on this, so I have 3 unknowns here. I don't know, or 2 unknowns, excuse me. I don't know acceleration, I don't know tension. So I need another object, which is going to be this round big pulley. And it's going to have tension pulling on it. And the important to know here is the radius from here to here is 0.6 meters. And it has a mass, let's see if it gives me 5 kilograms. So this is a 5 kilogram mass. All right. Well, this is being made to accelerate in a circular motion, and we know that torque equals I alpha, right? And so in this case, there's a tensional force on the edge of this that's 90 degrees to the radius. So really, there's 2 kind of torques mixed together here. You have a tensional force, a distance r from the pivot, and we don't have to use sine of theta because sine of 90 is 1. That's my torque, and that torque is working according to I alpha. All right. And then here I have tension minus 30 newtons equals 3 kilograms times negative A, and A is negative because it's going down. Now, I right here, look at that one little guy right there. I here is, you just have to know it, or I'll give it to you actually. For a solid disk, it's 1/2 mr squared. That's just what it is. And then alpha we know is A over R, right? That's the linear equation, or how we go from angular to linear. And then tension times R. And if you'll notice, all my R's will divide out. That will divide out with one of those. And this one will divide out with that one. And I'm left with tension equals 1/2 MA. Well, these 2 tensions here are similar. So I'm gonna use substitution. I have 2 unknowns, 2 equations, and I'm just gonna substitute in 1/2. I'm gonna make this capital M because this is a different M from the M of the bucket. And I'll put my numbers in here in a minute. Times A, both these A's are the same. Minus 30 equals negative 3A. All right, I'm gonna put in my numbers. 1/2 of 5 would be 2.5A minus 30 equals negative 3 3a equals negative 3a. So I'm going to add, or I'm sorry, subtract 2.5 to both sides. That's going to give me negative 30 equals negative 5.5a. Negatives divide out, and you're left with a equal to 30 divided by 5.5, which is going to be about 5.45 meters per second squared. All right, that is the acceleration of the bucket. That is the linear acceleration of this rotating disc. Now, if I wanted the angular acceleration of the rotating disc, that would be A over R. So I would take 5.45 and divide it by, that's meters per second squared, and divide it by the radius 0.6, and that gives me 9.1. So alpha would equal 9.1 radians per second squared. So 2 objects, I did a force diagram for each one. These are all done the same. All done the same. And let me extend the page here just a little bit. And it asks for, after it's fallen 4 meters, well, I want to find the speed. I want to find the speed after it's fallen 4 meters. So I could say v squared equals v naught squared, started from rest, plus 2a delta x. And I'm wanting to find v, so it'd be this, and this is 0. V naught, it started from rest, would be the square root of 2 times 5.45 meters per second squared times delta x, which is 4 meters. Let's see what I get. I'll do square root of 2 times 5.45 times 4. I get 6.6. So the velocity should be about 6.6 meters per second. Let's see what the answer is here. Number 52. Well, they give it in radians per second. So I'd have to divide by 0.6. And I get about 11, which is what they got. They got 10.9. I used 10 instead of 9.8. So omega would equal v over r, which would be 6.6 divided by 0.6 radius, which would be about 11 meters per second.